Good morning, all of you TyBscPhysics student. We have to see here our subject is solid state physics and we want to continue the fourth chapter, which is magnetism. In this lecture we want to start the next new point, which is the ferromagnetism. In last lecture we have to see here what is the property of the paramagnetism and what is the susceptibility of paramagnetism and the spin alignment value of this paramagnetism and whatever result which is see in the last lecture. In this lecture we want to see this ferromagnetism and ferromagnetism, if we see as the magnet or the magnetic property of the material which is referring as, so that capability of this material, which is the piece of iron which has ability to pick up the other pieces of iron. So that is mean by that ferromagnetic material have the capability to pick up the iron pieces or attract the iron pieces. So that material which is known as the ferromagnetic material, and that material we have to consider as the permanent magnet, as it exhibits the magnetic property even in the absence of the applied field. So this is the property of the ferromagnetic material, so that is the pick up the other iron pieces of the material which is considered as ferromagnetism, and that have capability or such material which is called the permanent magnet, and that shows the permanent magnet condition without that material which is presence of the applied field. So that is the absence of the applied field. And if we consider the phenomena that magnetization which is observed there, which is increases when the external magnetic field which is applied to the specimen, and that ferromagnetic material which exhibit the hysteresis loop. After some time we have to see that the idea of hysteresis loop, how it is working. See that sometime we have considered here, for example, of ferromagnetic material or ferromagnetism in considered as the ferrous, cobalt, nickel and gadolinium is mainly due to self alignment of groups of atom carrying a permanent magnetic moment in such direction in a such direction. So that is, we have to already know that idea. So that paramagnetic substance and ferromagnetic substance have a permanent dipole magnetic moment, but in paramagnetic moment that substance which shows the permanent dipole moment when this substance which is placed in the external applied field, but this ferromagnetic substance or material which have carrying the permanent magnetic moment, and a ferromagnet has the spontaneous magnetic moment. So that is considered as if that magnetic moment even in zero applied magnetic field. So that is, so that we have to know that other substances like diamagnetic substance, paramagnetic substance, that shows the magnetic moment when that substance which is placed in the external magnetic field, but in the ferromagnetic substance, that substance which shows the magnetic moment when it is does not apply the external magnetic field, and that existence of this spontaneous movement which suggests that the electron spins and magnetic moment which are the arrested in the regular manner. And if we consider in the below figure that except the simple antiferromagnet have spontaneous magnetic moment are called the saturation moment. So there are the different alignment of the simple ferromagnetic moment, simple antiferromagnetic and ferrimagnetic material. So alignment of the vector which is shown here, so that understanding this vector alignment we have to know that, or lattice parameter alignment we have to know that what is the ferromagnetic substance crystal alignment, what is antiferromagnetic, and how the type of the ferrimagnet. So if we consider here that in the simple ferromagnetic material, so that alignment of the vector which is up state and which is parallel to each other, and that in the simple anti-ferromagnetic material that spin alignment are opposite to each other, and ferromagnetic material which are also same type, but the magnitude of the vector, magnitude of the alignment of the vector which is quite different. So that analysis of this vector component, we have to see that vector component, that means that the component which is considered as the spin alignment of the up state or down state, that analysis of the structure which is ferromagnetic or anti-ferromagnetic or ferrimagnetic material. So with that idea we have to get that the simple idea of this material. So if we taken a ferromagnetic material, that spontaneous magnetization which is can occur below a certain temperature, spontaneous magnetization which is can occurs at a below temperature level. So that temperature which is known for the Tc, that the Curie temperature, and that is known as the ferromagnetic Curie temperature. And above the Curie temperature, the ferromagnetic material which is acts like a paramagnetic material. So this is very important point. So above the Curie temperature, that below the Curie temperature, that material which is known as the ferromagnetic material, and above this Curie temperature, that material which is acts like as a paramagnetic material and has susceptibility which is given by the law, that is Curie-Weiss law. This is very important law, which is also seen in the statistic mechanics, which is also study of this law which is in the very detail. So that Curie law which is considered as chi is equal to C divided by T minus Tc. So above the transition temperature, the ferromagnetic substance become paramagnetic. Above the Curie temperature, ferromagnetic substance becomes the paramagnetic, because then the parallel spinning of the energy is sufficient to overcoming the randomizing effect. And we have already seen that that above the Curie temperature, so that ferromagnetic material which is acts behaves like as a paramagnetic substance. And in below table we have to indicate here the Curie temperature of major ferromagnetic materials which is considered as for example, see here the element which is considered as the Fe, electronic configuration which is 3d6,4s2, and crystal structure which is considered as the BCC, and magnetization at 0 Kelvin temperature, magnetization which is considered as 1.7 into 10 to the power 6 ampere per meter, and temperature range which is given as 1043 degree Kelvin. And say cobalt, nickel and gadolinium, and with respect to electronic configuration, crystal structure and temperature of given this substance which is here, which is considered as the ferromagnetic material. And that table which shows that the ferromagnetism which is not exclusively characteristics of the crystal structure, and they have wide range of the Curie temperature and noticeable range of the magnetic moment, which is such as variation of 1.7 into 10 to the power 6 up 1.4 into 10 to the power 6 for cobalt, nickel 4.48 into 10 to the power 6, and gadolinium which is considered as 5.6 into 10 to the power 6 7, and are corresponding to this temperature. So that one common thing in this year, if we say have to electronic configuration, so that consider that electron which is occupied in the D shell and S shell, so that corresponding to this, and in this 3D transition of group or other in the 4F, that are the rare earth transition group. Okay, and this is the existence of the partly filled D or F shell which is the essential. So this is the necessary condition for this ferromagnetic material. So next very interesting point is where the ferromagnetic domains, because we have to know that depends upon this ferromagnetic material, that very popular theory which is considered as the domain theory, and alignment of this domain theory which has moving to the field direction or not, or opposite to field direction. That analysis of this, we have to more clear that idea for the ferromagnetic material with the help of this domains theory. So that the property of this domains which is considered here, so that paramagnetism which is occurs when the paramagnetic ions in a solid and that lock together in a small region which all magnetic moments along the same direction, so such region is called the domain. Okay, so that is, these are the very microscopic property of the material, and that small region, very small region which is considered, that have the dimension which is given as that volumes of this domain which is considered as -12 to -8 meter cube, and contains 10 to the power 17 to 10 to the power 21 atoms in each domains. So that very small region which is considered as the domains, and the boundary between the domains having the different orientation are called the domains all, which is very grateful show in the figure first, that is the alignment of the domain, and between this domain alignment there is a boundary between that boundary wall, that is called as the domain wall. Okay, if does not this material which it does not place in the external magnetic field, so that this sample of the ferromagnetic material, that domains which are considered as the randomly oriented for randomly oriented direction, and such material, that material which is not placed in the external magnetic field, so that net magnetic moment of this material is 0. Net magnetic moment of this ferromagnetic material is 0, which is shown in the figure A, that is known as the without external field. So that domains direction is everywhere to each other, and if we this sample which is placed in the external magnetic field, that domains which is aligned in the field direction, this domains which is aligned in the field direction, so that is have the net magnetization moment which is shown in the figure B, that is external magnetic field. So see that here, so that domain theory, for the domain theory, that domain contains very small size which has considered the volume of this cell which is considered as 10 to the power -12 to 10 to the power -8 meter, and each domain cell which is considered as the atom consists of 10 to the power 17 to 10 to the power 21 atoms in each domain, and this material which is not placed in the external magnetic field, that have 0 magnetic moment, and if we place in the magnetic field, that have magnetization and also magnetic moment, and these domains which are and this vector which are moving in the field direction. So this is the idea about the orientation of the domains. Now this experimental observation, if we see here, that external field is applied, so what is the domain alignment of there which is shown is there, so we have to see here. So those domains are aligned with the field direction, grow in size at the expense of less favorably oriented domains. Okay, so that is, we have to already see that if external field applied, so that domains which is alignment in the field direction, and if external field is very strong, then domains are aligned along the field direction and provide high observed magnetization value is there. So if field is high, then magnetization value is high, and when the external magnetic field which is removed, then the sample may return net magnetization in the direction of original field at the ordinary temperature. Thermal agitation is not sufficient to disrupt the alignment to the random alignment. So that is considered for this figure. So if we place this material in the external magnetic field, they have same alignment which is moving in the field direction, and if we remove this magnetic field, so that material which is retaining in the original position. So if the temperature of this ferromagnetic material which is increased, the temperature of ferromagnetic substance which is increased at high sufficient temperature, this domain structure break. The possibility of this domain structure which is breakdown, and we have to say that here this ferromagnetic material becomes behavior as a paramagnetic material, and that which temperature that such material which has the change the property of the material, so that temperature which is called as a Curie temperature. So if we consider the example of these ferromagnetic substances which is considered as iron, cobalt and nickel, all that is all transition group element. These are the all transition group element. So are ferromagnetic at sufficient low temperature. Already we have to say that temperature at low temperature we have to consider that this is the ferromagnetic material, and that if we go further in increase the at critical value of temperature increases above that value, so that material which is behave like as a paramagnetic material, and that rare earth such as the gadolinium, terbium are the ferromagnetic below the room temperature, while the other rare earth are ferromagnetic at the low temperature. At the sufficient high temperature, all transition and rare earth metal becomes a paramagnetic. So this is the very important property. So that is property, if we increase the temperature value, so that ferromagnetic material which is acts like behavior as a paramagnetic material. And for ferromagnetic substance, the spontaneous magnetization is maximum at the T is equal to 0 degree Kelvin, drops to the 0 at the temperature, that is the critical temperature, and this temperature is called as the Curie temperature. And this plot of the spontaneous magnetization which is against, we have to see that here the at the horizontal axis which is considered as the range of the temperature, and vertical axis which is considered as the magnetization. And if we see at horizontal axis, if temperature range is minimum, that substance which is like as a ferromagnetic material and have high magnetization value, and if we increase the temperature value, so that magnetization value which is suddenly drop is low or going to 0, so that is known as this temperature effective value, so that material which is acts as a paramagnetic material. So next main point which is considered as a hysteresis. So that hysteresis which has show the property of the material when it acts like as a ferromagnet, if we, and what is the field direction, and if we increase the value of the magnetic external magnetic field, then what the change of the material, and if we remove this external magnetic field, then what happens there, which is shown in the hysteresis loop. So consider here a large amount of information can be obtained about the magnetic properties of a ferromagnetic material by studying the hysteresis loop. Okay, so whatever property of the material that is considered as the magnetic property, which is studying for the help of this hysteresis loop, and this hysteresis which is coming word from the Greek word, and that means that the latter, and refers that the retardation in the response of the material to a change of the applied field. So that means that here idea gives, so that in hysteresis loop idea which is considered as latter means that the after external magnetic field, what is the change of the properties of the material in, so that which is considered here. And if we remove this external magnetic field, then what property changes, which is also here and which is shown by the BH curve. So if we see the magnetic field induction, that is B bar, that is unit which is considered as the Tesla, and magnetizing intensity which is H, that the typical hysteresis loop, that is the BH curve, which is shown in the figure we have to see here. So in the figure we have to see that intensity, magnetization intensity, which is placed on the horizontal axis, and magnetic field induction, that is shown on the vertical axis. And by increasing the value of this, what is the change of the structure, we have to see here. So if we consider the loop is generated by measuring the magnetic flux B while the magnetizing force is changed. So that is mean by, if we increase the magnetic field induction value, that is B value, so that magnetic field is there, the magnetic flux also there. And if we this increase the field, that increasing the flux, and due to the increasing this flux, we have to increasing the value of the magnetizing force, or what is our change there. And then fresh ferromagnetic material is magnetized. If we, you have to know that if we any substance or that metal substance which is placed in the external magnetic field, so that material we have to get the property, that material which is got to magnetize. And what is the property of magnetize? That material which has achieved or pick up the pieces of the iron to each. So that material which is considered as the magnetized material, and it will be magnetized along the dotted curve which is shown in the figure. So that is curve which is shown in figure. So that dotted line which have show the magnetizing property of the material. Okay. So at point A, almost all magnetic domains are aligned in an additional increase the magnetizing force. So that is mean by, if we increase the if we substance which is placed in the external magnetic field at the high value, that substance which has shown the magnetizing property, so that substance which is considered as the, that property which is considered as the A position. So that all ferromagnetic domains which are aligned in the additional increasing of the magnetizing force will be produce very little increase in the magnetic flux. Okay. And the material has reached that point, the magnetic saturation, when magnetic intensity H which is reduced to 0. So that have show the property, and the material is demagnetized along the path AB when H is equal to 0. Okay. So that point A which is reach magnetizing value, and if we replace the magnetic field, so that hysteresis loop which path show is here A to B, and that point A to B when the magnetic intensity value which value is 0, then curve path show as the position A to position B. So that is here. So that path which is show A to B, and when B position, then magnetic intensity value is 0. And if C is here, there is some magnetization remaining in the material, that's shown by the point B, and this point is referred as the retentivity and indicate that the remains or level of the residual magnetization in the material. So that is mean by, if we that material which is replaced in external magnetic field, that is not magnetic field is there, but if we once that material is magnetized, and if we remove the external magnetic field, that material property which has hold some magnetization or some magnetizing value, or that material having the magnetization or magnetized material, so that have show some magnetic property, so that property which is referred as, or that magnetization which is referred as the material which is considered as the retentivity. Okay, retentivity that consider here some magnetization remain in the material shown by the point B. So this point B which is considered as the retentivity. Okay, and if we see as the magnetic intensity H is reverse at some negative H, the flux in the material becomes 0. Flux in the material which is becomes 0, and the point C which is known as the call point is coercivity. So we have to see that. So that magnetic, what is say that the negative H value, that is magnetic field strength value is negative on remove, the flux of the material which is 0, and this value which is comes to the that path which is shown in the B to C, that on the C axis, that the field strength value, that magnetic field strength value H is 0, that is negative, and this value or this point which is considered as the coercivity on the curve, and the magnetic force which is required to remove the residual magnetism from a material is called the coercivity force. So that is shown here. We have to already see that if we material which is placed in the magnetic field, so that material is the magnetizing material, and that shows the high saturation point, that is considered as A. And if we decrease the value of H, so that point which is on the vertical axis at point B, so that is the less value of H, that is 0 value, and that point of the dotted line is B. But that point, that material have holding some magnetism, so but at point negative value of this H magnetic field strength, so that overall magnetism value or overall magnetism of this material which is reduced or replaced, so that point which is called as the coercivity, and that corrosive force of coercivity of the material which is the considered as the removing the residual magnetization or magnetism. If we consider all the magnetizing intensity H is further increased in the negative direction, so that show in the graph, that point D. What? So that magnetizing intensity H is further increased in the negative direction, that is point C, that graph show by point C to traveling to D point, and that negative direction of the D value or H value, the material will again the magnetize or magnetically saturated, and but in the opposite direction, that at point A which is shown in the positive direction, and at point D which is considered as the negative direction, but this material will gain also its magnetic property, and that material we have to consider say that the material is the magnetized, but also change here, so that material which is considered it will gain become the magnetically saturated, but in the opposite direction, so that reducing this H value to 0 brings the magnetization to a point E, so that is shown on the B magnetic field induction B at the vertical axis at here, that point below upon the 1.02 between minus 1.5, that point E, and that is brings to magnetization to point E on the curve which is increasing the H in the positive direction, so that curve which is increasing in the positive direction, so this will decrease the magnetic flux, that is B value 0, and H value which is increasing strength value, and that considered as the H along the positive direction, and that material is again saturated point A of this material. So this is the curve path of that path traveled by the curve as A to B, B to C, C to D. So that path A to C or B to C that have value has reduced the magnetization property. Again this value negative of H value going to D, so that have some deflection of the magnetizing property of the material which increase, and this graph by negatively increasing the value of H, that value positive direction along increasing, so that have again show the property of magnetizing material, and again that point A, so that loop is complete, this loop is complete, so that loop which is considered as the hysteresis loop, and this material which is never return to the O point. Okay, so this is known as the hysteresis loop, and we have to property of this, we have to got understanding the idea about our concept about understanding the what is meant by this hysteresis loop, and how that material which has shows the different property at the different point, and how to complete the property of the hysteresis loop which is see here, and that the value of the coercivity ranges over 7 orders of the magnitude, and it is most sensitive property of the ferromagnetic material which is the subject to control the coercivity. Okay, so this is the very grateful idea of this hysteresis loop. So next point which is see here, the anti-ferromagnetism. What is meant by the anti-ferromagnetism? So that anti-ferromagnetism which is considered as the material which show the interesting modification of the ferromagnetic behavior. So this point, what is meant by anti-ferromagnetism, what is meant by ferromagnetism, Nil temperature, which is see in the next lecture. Thanking of you.